All right, first order of business, we'll take a look at the ChemQuest. This one's not very long. It's a lot like what we did last week as far as the procedure and what it is you have to do for the work itself. So I guess the new word is hydrate. And when you look at a hydrate, it might look like this. It might look like this. The idea is it's more like this, where the tennis balls would be kind of like the main structure, and then all of these, what would be, if we had them color-coded, would be water molecules, are somehow attached to the outside of it through intermolecular forces. But it's that combination, and lots of the compounds we've actually used have already been this way, considered hydrated. Are different things we can look at. So if we look at some of this this guy right here, so the calcium carbonate, if this is calcium carbonate as a hydrated form, this would be called calcium hexa hydrate. Hexa meaning 6 with our 6 H2Os attached to it. So what we're going to be doing is we're going to be using the empirical formula to figure out that guy, to figure out the number of moles in this ratio of this anhydrous salt to the water when they're in combination. All right. One thing to remember is that we're not multiplying these together. These are just attached to each other, much like these structures up here are just kind of like surrounding the molecule itself. A good picture of that is right here. All right, so this one would be like a copper nitrate, and one of its hydrates is a 3. So we have these 3 water molecules surrounding it to buffer it, to attach water to it, to give it some more structure, and then we can use that in many different ways. But the idea is that we're going to try to figure out. We're going to know, but the part that we're not going to know is we're going to have this unknown amount of water. Okay, so a problem might read like this. We have a hydrated salt of calcium chloride with its molecular structure being CaCl2 with our dot, and then N, so that unknown number of moles of H2O. In the lab, we took 2.4 grams of hydrated CaCl2 and heated it strongly. After heating, all the water was driven out of the crystal, and the remaining mass of the anhydrate was 5 grams. What is the formula for the hydrate? Right. So this is our key. This is what I'm going to be asking to solve for, a few different times. And the nice thing about it is once you have the info, it looks a lot almost exactly like it did last week. All right, so a couple things we need to know. We need to know about both the anhydrous salt and the water, and we need to know how much of each we have so we can do our empirical formula. With the information we have in this problem, we have this total. This is the hydrate. We found out after everything was gone, we found out what the anhydrate was, and the combination of those two, looking at the work done here, if we take the total minus what we have remaining, we can figure out what we lost, and what we lost is 3.24 grams of water. Okay, and so once we know the grams of our water and the grams of the hydrate, we can make this very similar looking problem where we take the grams, and if we want to compare them because we want to find its structure, we want to find its formula, if we take the grams divided by its molar mass, come up with moles. If we take the grams divided by its molar mass, come up with the moles. All right. So notice the only real difference is here we have compounds, and we're finding compounds. And last week we just had elements to find a compound. We're just taking compounds to find a bigger compound this time. So in the end, we're going to use this number and this number again, and we're going to divide by whichever one is the smallest, right? So in this case, this guy is the smallest because it's 0.04. Don't, obviously be careful with your calculator. You wouldn't want to screw that up. So when we do that, we end up with water equaling 4 moles, right? And our calcium chloride, or anhydrous, the stuff that was still left, that white powder, if you will, would be 1. And so the ratio is 1 to 4, and we'd write that this way. So that n becomes this guy. It becomes that 4. Okay, so I laid this problem out for you. I'll do another one, a separate problem on a sheet of paper so you can actually watch me work it out. But it's really the exact same steps. And that's why I only have 3 problems for you, right, of differing degrees. But this one is pretty straightforward. I'm also going to ask you to find the mass, the percent mass of H2O. And remember, for that, it's just the part over the whole. All right, so we'd find the percent of water, and there's a couple different ways to do it, so you can try that out, but that's no different than before. Same thing with this one. I'm going to do the same thing. This one starts out different, but really it's the exact same thing. This one, instead of giving you the masses, I just gave you the percentages, and we know how to deal with that. You can just turn those in to masses. I guess the difference on this one and this one is you got to make sure that you solve, what is sodium sulfate? Make sure you balance charges. What is iron sulfate? Make sure you balance charges, right? Use those. And then there's some review questions. Again, this is just to help us get ready. An empirical formula problem, a percent composition problem where all you're finding is the oxygen. And then from there, we have some of the ones where we have to go back to atoms. So in some of these, you'll have to use Avogadro's number again. So again, make sure you get on this early. I put these back in there because obviously a few of us had struggled with them. So it's another way for you to try and me to help you out through this chem quest. So you can see it's really short. It's kind of one new concept, which is good because then our skills practice is short, but we have a lab added this week. So have fun and see you in office hours. Bye.